We continue to discuss applications of continuity equation by considering different examples, different problems, so that we see that in how many ways continuity equation can be applied to different fluid flow situations. And earlier we discussed a two-dimensional flow, and now we move on to consider an example or an exercise of three-dimensional flow. And of course, it is a simple example. All these examples are taken from Fluid Mechanics by Sengel and Simbala. That I am referring this, I am taking this for this course. And therefore, if you see the reference number or something given, they are referred to the book, and these exercises are also taken from that book. I have said it earlier, and I have just said it for the sake of a reminder, a simple reminder. The problem posed here is that two velocity component of a steady, that is no time dependence, incompressible, no change in density, but three-dimensional flow field are known. So two components are known. They are U is given as this value, and W is known. So obviously what is missing is the V component. The V component of the velocity is missing. So where A, B, C are some constants, the Y component, the Y velocity component, which we represent by V, is missing. And they say the question is, the problem is, determine it. Generate a function for this. So we have to find it, and of course the only tool that is available to us to determine it is continuity equation. And continuity equation, when we consider the three-dimensional flow, will be du by dx, dv by dy plus dw by dz equal to 0. So when we consider the solution, just the problem is enumerated again, is written down. We need to determine the y component, and of course we need to use the given values that have been given to us in the question. The assumption is flow is steady, so d by dt is 0 for all the terms that may occur, and the flow is incompressible, so d by dt or variation of rho is also 0. Since the flow is steady and incompressible, and since we are working in Cartesian coordinates, we consider the equation that I just wrote down, which was du by dx plus dv by dy plus dw by dz equal 0. From these two, if we retain dv by dy on the left hand side and take the other two terms on the right hand side, we have, this is what we get. And from the given values of u and w, when we differentiate this, the contributions that we obtain are 2ax and ax plus 2byz respectively. So we will be left with dv by dy is equal to minus 3ax minus 2byz after summing up all the terms. But our question was to determine v, and when we want to determine v, all we have to do is now, since this is derivative of v, if we integrate it with respect to y, we will get v. So integrating it with respect to y will give me minus 3ax times y minus 2bz into integral of y, which will be y square by 2. 2 and 2 cancels out, and we are left with only by square z plus some constant of integration. And constant of integration in this case can be, we can keep it as some function that depends on, not on y, but on the other variables that are occurring here, x and z, possibly. Not necessarily, it can be an absolute constant, but we don't know, and for the sake of generalization, we can keep it like this. And you can see that if I differentiate it with respect to y again, I will be obtaining this term. So there is consistency and there is no problem. And you can see, and that is why this remark that in fact any function of x and z will give us this value, so we can have this as constant of integration. This is what we have seen, the three-dimensional flow situation that was given to us, and from this the unknown component has been determined. And that is the way that we determine the unknown components by using continuity equation.